Have you ever done a PET scan? Ever wonder what's going on inside one of those things? Something that PET scanners and lightsabers have in common is that they both need very special crystals in order to work. In this video, we're going to talk about these strange glowing crystals inside our PET scanners. But first, I want to remind you about the newsletter. Check out the newsletter to read the entire scripts for previously released videos, including those you might not have seen before. The sign-up link is in the video description below. I try to put one out every week, maybe two. Alright, back to the show. A relatively recent technology, the positron emission tomography machine, scans the human body using a radioactive substance called a tracer. You start the PET scan by first injecting the tracer into a person. The tracer, usually made up of an isotope of fluorine combined with carbon, nitrogen, or oxygen, then circulates throughout the tissues inside that person's body like as normal. The tracer contains a radioactive atom that is rapidly decaying. As that atom decays, it ejects positrons from its nucleus. The positron is the electron's antiparticle counterpart. It has a positive rather than a negative charge. The positrons travel for a bit, maybe a millimeter, before colliding with the electrons inside human tissue. When this happens, the positron and electron annihilate each other, in the process emitting two 511 kiloelectron-volt gamma photons. These high-energy gamma photons are very likely to exit the body, so the PET scanner is basically a set of detectors positioned around the patient trying to capture these gamma photons exiting their body during the scan. The scanner then turns these photons into an electrical signal that can be visually transformed into an image. That is your PET scan. PET scans can extend the capabilities of other machines like CT scans or MRI scans, and are often used in conjunction with one another. What makes it special, though, is its insight into how the human body is picking up and processing chemicals. Why is that important? It shows us metabolic activity. How fast is the body or something inside the body consuming resources? For instance, there is a version of a PET scan in oncology that takes advantage of a tumor's rapid uptake of glucose to measure a tumor's growth. PET scans can also help reveal the progression of certain brain pathologies like Alzheimer's. When it is operating normally, a healthy brain uses a lot of glucose. So when it doesn't pick up that glucose as fast as it used to, that can be an indication that something is wrong. The whole scan does not work without the detectors for these high-energy photons. Your average PET scanner has thousands of what are called scintillator crystals set in rings surrounding the patient. They are called as such because they demonstrate scintillation. Scintillation is a derivation of the word scintillating, which means to shine brightly or to be brilliant or excitingly clever. Basically put, the crystal is kind of like that sword that Frodo has in the Fellowship of the Ring, Sting, except it lights up to ionizing radiation rather than orcs. Why does it glow? When a photon hits an atom, several things happen. One thing is the photoelectric effect. The photon transfers its energy into one of the atom's electrons on its outer shell, sending it flying outwards. This photoelectric effect is the very effect that makes image sensor chips possible. I briefly discussed it in my video about image sensors. We collect the electrons and then use electronics to interpret them and create an image. If the photon has a little more energy than that, like a 511 kiloelectron-volt gamma-ray photon, then upon collision with an electron it transfers over only a portion of that energy. After the energy transfer, the photon bounces off, possibly to hit other electrons, like a zombie searching for new hosts. The energized electron leaps out of its current location in the valence band into a higher band of orbit, the conduction band. This energized state cannot last forever, so the energized electron eventually returns to ground state in the valence band, emitting its excess energy. This excess energy is usually emitted in the form of ultraviolet photons, which we cannot see. So, in order to get the crystal to emit visible light, we need to change it in some way. We do this by adding an impurity to the crystal, or in other words, to dope it. So now when the electron returns to its ground state and emits its energy, what it emits can be visible. The crystal itself is just one half of the odd couple driving our PET scanner. What about the systems detecting the light coming out of the crystal? The scintillator crystals are attached to photomultiplier tubes that multiply and convert the weak scintillation light into electric pulses for interpretation by electronics. These are cheap and extremely sensitive electronics that turn a single photon signal into a significant electric one. Originally, we used to have one tube to one crystal, but these tubes are quite big, and due to size concerns, the industry moved to a block format with one tube servicing several crystals. Though today, there are silicon-based semiconductor variants that do the same jobs. In order to be suitable for a PET scanner, scintillation crystals have to have several special requirements. First, they have to be really good at stopping and interacting with these gamma photons. This is in large part determined by the material's density. The higher the density, the more probable it is that the photon collides with an electron and triggers the photoelectric effect, a probability referred to as the photoelectric fraction. Dense is good because it is pretty likely that these photons pass right through the crystal. These crystals' photoelectric fractions for 511 kilo-electron-volt gamma photons are universally less than 50%. They also need to be really good at converting that ionizing radiation into light. In other words, they should have a high light yield. There are actually two types of scintillator crystals, organic and inorganic. All PET scanners use inorganic crystals since they have better light yields, and apparently because the organic ones smell. Anyway, the higher the yield, then the less radioactive materials we have to inject into the patient. The less radioactive materials we inject, the less likely we are to get Spider-Man. Third, the crystal's light has to have good spatial resolution. In other words, we need to be able to determine where the gamma ray entered the crystal. This helps give us a better, clearer image. Fourth, the ideal scintillator crystal should have a low decay time, sometimes also known as fast kinetics. In other words, how fast a crystal's light fades away after it absorbs the gamma photons. A low decay time essentially helps us get a higher quote-unquote refresh rate of observations. Such information is helpful for more advanced PET scanners like 3D PET. And lastly, of course, the crystal has to be cheap to make and use within the PET scanner itself. The reason for this is obvious. We need a lot of them. Considering the length of the wish list, there is no such thing as a perfect scintillator crystal, but that hasn't stopped the industry from trying to find one. The scintillating phenomenon was first discovered in an experiment involving water and radium back in 1903. 5 years later, the Kiwi physicist Ernest Rutherford used a screen made of zinc sulfide to observe the scattering of alpha particles. This was the first time anyone used scintillation to help observe the atomic structures. Then, in 1949, physicists discovered the first high-performing scintillator crystal, the thallium-doped, or thallium-activated, sodium iodide crystals. Over the next 35 years, that thallium-doped sodium iodide crystal would be the historical standard. Early PET scanners used this crystal throughout the product's development. But the crystal's big drawback was its relatively low density, about 3.67 grams per cubic centimeter. This means less stopping power and fewer captured gamma photons, which limits the device's imaging quality. So it was very exciting news in 1973 when physicists M. Weber and R. Monchamp announced the discovery of a new scintillator crystal, bismuth germanium oxide, or BGO. BGO is far denser than sodium iodide, 7.13 grams per cubic centimeter versus 3.67. Combine with the highest atomic number for a scintillator yet discovered, and you get a crystal with some real gamma-ray stopping power. BGO's big physical downside is its low light yield, just 9,000 photons per mega-electron volt versus sodium iodide's 38,000. The crystal's light deficiencies would need to be made up for by the photomultiplier electronics. BGO also has a very long decay time, 300 nanoseconds versus sodium iodide's 230. Again, a long decay time is like a slow refresh time on a television. Furthermore, years would pass before the PET scanner industry became capable of receiving the crystals in a high enough volume necessary for adoption. This finally came via science work done starting in 1989 for the CERN Large Electron-Positron Collider, one of the world's biggest accelerators. The L3 experiment, as it was called, involved 11,000 or 12,000 24-centimeter long BGO crystals attached to silicon photodiodes. They were produced in China by the Shanghai Institute of Ceramics using the Bridgman method. The Bridgman method involves mixing pure bismuth-3 oxide and germanium dioxide together in a platinum crucible and heating it up in an oven to create a molten melt. We then slowly remove the heat from the melt from one end, where a seed crystal is placed, towards the other end. This is known as directional solidification, and I talked about it in my video about solar-grade silicon. At the end of this, we have ingots of BGO crystal that we can cut up and polish. The Bridgman method is also used in the semiconductor industry to produce crystals of materials like gallium arsenide, where the Czochralski method is unavailable. The learnings from the L3 experiment made BGO economically viable in the PET scanner industry. Throughout the 1990s, BGO took over from the venerable sodium iodide to become the standard PET scanner scintillator crystal with some 50% market share. Up until now, scintillator crystals were discovered through pure dumb luck. But in the 1990s, people started using their knowledge of how scintillation actually works to guide their search. And in the 2000s, two new crystals emerged to make up for BGO's light yield shortcomings. They are, and get ready for this one, lutetium oxyorthosilicate doped with cerium, or LSOCE, and lutetium yttrium orthosilicate doped with cerium, LYSOCE. They are dense, 7.4 grams per cubic centimeter. Their light yields are very good, 30,000 photons per mega electron volt, and their decay time is a huge improvement on BGOs, about 38 nanoseconds compared to 300 nanoseconds that BGO had. Most commercial use LYSOCE crystals are grown using the Czochralski method, the semiconductor industry's preferred method to produce single, perfectly structured silicon crystals. We create a liquid melt in a crucible and slowly pull a crystal out of that melt. LYSOCE is exceptionally difficult to grow using the Czochralski method. It is made up of 4 oxidized ingredients that don't go easily into that hot melt. 3 of them, yttrium oxide, lutetium oxide, and cerium oxide, melt at 24,000 degrees Celsius or higher. That is 5 times the temperature of the surface of Venus. At these temperatures, we risk melting the iridium metal crucible itself, causing contamination, and we have to implement special measures to prevent the oxygen from disassociating. Starting in the late 2000s, national security requirements triggered a flood of money into the scintillator crystal space. These requirements involved new scintillator crystals for X-ray scanners and radioactivity detectors. These products might not be used the same way as we use PET scanners, but they work similar principles and want similar things. Combined with our improved knowledge of the scintillation phenomenon, we have more crystal options than ever before. New publications of crystals with light yields over 20,000 photons per mega electron volt have doubled in the 2010s. Scintillator-based PET scanners remain the standard in the industry. However, people continue to experiment. There has been interesting research into silicon pad-based detectors for PET scanners. Prototypes have been manufactured, and those seem to work. However, there are many technical challenges to overcome. First, they would be very technically complicated to build. And second, they would probably not work as well as traditional crystals. The best their image quality might be suitable for would be like preclinical scans. This is because silicon's photoelectric fraction is nowhere near as high as the scintillators like BGO. BGO's is 43%, while silicon's is less than 1%, which forces us to make the pads thicker to compensate. So, no CMOS PET scanner chips just yet. But semiconductor silicon has already replaced traditional photomultiplier tubes in enhancing the data we can read out from the scintillator crystal. At the same time, there are a few researchers who believe that we have gone as far as we can on ultra-pure single crystal solutions. So, they're looking at solutions that incorporate nano-sized crystal particles, mashing them with electronics just like how an image sensor pixel has a silicon photodiode and transistors. That is very interesting. So, for the immediate future, there is no risk of us replacing PET scanners with some nifty compact silicon chip. The search for the perfect scintillator crystal continues on. PET scanners of the future will combine newer, better crystals with powerful new techniques in digital image processing to create incredible, more data-rich images. The future, literally, glows brightly. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the newsletter, and I'll see you guys next time.